Okay. Okay, fine. Let me share the PPT that we were discussing in the last class. So I hope the presentation is visible to you. And let me put it in the full screen mode. And, fine. The topic of the discussion is synthetic curve, which is the second part of the second unit, right? And of course, we already started this topic in the last class itself. I think last two classes we were talking about synthetic curves only. And all these topics are already discussed, different, curve representation methods. All these things were already discussed, and we also understood the differences between non-parametric and parametric, and again, what are the advantages of parametric form and compared to the non-parametric form, and all those things we already discussed. All these slides you can easily understand, right? The limitations of non-parametric and the advantages of parametric curves. All these things are completely discussed. Even all these markings are related to the last class. Okay. And in the last class, if you, I told you that synthetic curves, there are like four varieties of synthetic curves are there. So out of which Hermite cubic, of course, on top of that, there may be a more number of synthetic curves also, but these are the very basic synthetic curves for our discussion. Out of which the last class I discussed about Hermite cubic spline and all the mathematics behind Hermite cubic spline, its parametric equations, matrix form, and we also tried to solve a problem. Okay, uh, so what are maybe the kind of synthetic curve? Most of the synthetic curves do have the common characteristics like control points. Every synthetic curve do play with the control points are also called, and global control is possible in case of eccentric curves, which means you can alter the shape, you can play with the curve, and it's also like flexible, more flexible, right? And you can play with the order of the continuity as well. And I also told you about different types of continuity, C0 continuity, C1 continuity, C2 continuity, all those things were also discussed in the last class itself, like curve generation and continuity. These pictures do help you. We discussed. I'm just recapping of whatever that we discussed, right? So basically, curves can be, you can also categorize in two ways. Like the first one is interpolation, right? The second type of curve is approximation. Interpolation is something like whatever the control points that you pick on the screen, the desired curve, synthetic curve, it passes through each and every control point. So if that is the case, then such kind of curves are comes under interpolation. Whereas in certain other synthetic curves, the curve may not pass through. It need not pass through each and every control point, but it approximates all the. It takes care of each and every data point Am I audible?
Yes, sir.
Yes, sir.
Some network issue actually. So anyway, let me resume the PPT. So I hope it is visible to you right now, right? So we also discussed about different types of continuity, like C naught continuity means various segments of the overall curve do meet each other at some common points. So whereas in case of C1 level, they not only the segments not only meet or intersect, but also maintain a common tangent at the intersecting points in case of C1 continuity, whereas in case of C2 continuity, on top of the common tangency, they do have common center of curvature, which means the radius of curvature is same for both the curves at the intersecting point. So these are the basic continuities which are sufficient enough for most of the synthetic curves. But in a particular or in a special synthetic curves, they may need to go for a higher order continuities as well. But otherwise, these C2 level is more than sufficient. That is the reason cubic curves of the mathematical make cubic curves. You get some issue. Some issue. I hope I'm audible. Am I audible? Okay, okay. Please bear with me. Some network issue. It's keep on rising. Fine. And I also explained about the mathematics behind the zero order continuity. All these things we already discussed. So I don't want to get into the explanation part again. I, so second order continuity, and now Hermite cubic spline also was discussed in the last class. The parametric equation of Hermite cubic spline is like P of u is equal to sigma I is equal to 0 to 3, which because it's a cubic spline. I is equal to 0 to 3 ai u to the power of I, and u is varying from 0 to 1. This is the expansion of this sigma form is nothing but P of u is equal to a naught plus a1 u plus a2 u square plus a3 u cube. All these things are that's the expansion. And Hermite cubic spline, this particular Hermite cubic spline, the inputs for this are like two endpoints, P naught and P1, and P naught dash and P1 dash. Totally four inputs are given in case of a Hermite cubic spline. P naught and P1 are the two endpoints, whereas P naught dash and P1 dash denotes the tangent vectors at the corresponding endpoints. So if those four endpoints are given, how to solve this, the parametric equation, and then how to attain this matrix form, all those things were well discussed in the last class. And also subsequently the blending functions. Those the blending functions are nothing but the coefficients of P naught, P1, P naught dash and P1 dash. The coefficients, which is nothing but 2u cube minus 3u square plus 1. This is one blending function. Similarly, totally four blending functions are there, and their behavior, B0, B1, B2, B3, their behavior, how it varies with respect to u. When u is varying, how B0, their blending functions are changing. How why we talk about blending functions is they influence the overall shape of the curve. Okay, if B naught value is more, nothing but it is taking care of P naught, the point P naught, the influence of P naught would be much higher if B naught value is more. So like that, why? Because that's the coefficient, right? So like that, the blending functions do influence the overall shape of the Hermite cubic spline. Similarly, some examples of the Hermite curves are also shown, and drawbacks of the Hermite spline, and some example also was discussed, right? If P naught, P1, P2, P naught dash and P1 dash, if 4 points are given to you, how to derive the Hermite cubic spline equation, and also how to identify various points on the various intermediate points on the Hermite cubic spline also were discussed in the using some example, right? I hope you can recollect whatever the points that we discussed till the last class. And today we are the point of discussion. The topic of the discussion is going to be Bezier curve, which is another important synthetic curve, and is being used by majority of the in majority of the cases people do use Bezier curve. And unlike I told you that the curves can be categorized into two ways. Like one is the interpolation, the other one is approximation. Interpolation is something like if the curve passes through all the control points or the data points, then the interpolation. Just like the Hermite cubic spline, if you look at the Hermite cubic spline, the initial point and final point were given as an example. 2 points are there. So the curve is passing through those given 2 points. Okay. Similarly, if 4 points are given to derive the spline, then the corresponding spline also would pass through all the 4 points. Whatever how many the spline always passes through all the points. So only difference is the degree of the equation will change depending upon the number of control points that you pick. Those splines belong to interpolation kind of a situation, whereas Bezier curve doesn't come under interpolation; it comes under approximation. Okay, approximation means the curve need not pass through all the intermediary points, but only thing is it passes through the first and end point. But if you pick intermediate points, the curve need not pass through the intermediate point. So Bezier curve belongs to such approximate category. Here, if you try to understand some of the Bezier curves from the diagrams. The first one is a linear Bezier curve. I hope the animation is visible to you, right? Here the t is varying from 0 to 1. T is something like a u. Okay, instead of u, here the picture used the parameter as a t. So at p0 is a 1 point, p1 is another point. So if 2 points are given to you, u is varying from 0 to 1. So in that case, the red color one, the dark color dot, that denotes various points on the curve. Okay, of course here it is a straight line. The Bezier curve becomes a straight line. Okay, it's in linear form and only 2 points are given to you. So it's simply a kind of a x equation and the y equation, just like how the straight line parametric form p of u is equal to p2 minus p1 p1 plus p2 minus p1 into u equation that it last class in the previous classes for parametric representation of the analytical curves. During that session we discussed. So if u varies, always that dot, black color dot, always moves in a linear manner. So that's the reason the red color one gives you the shape of the curve. So when parameter t value, it is changing from 0 to 1, you are actually getting a straight line, that red color one. Whereas in case of if you take rather than 2 points, if you take 3 points. Now if you take 3 points, so look at how the Bezier curve is, that red color one, it is showing you the Bezier curve. Okay, that black color dot shows you the point, any point on the Bezier curve at a particular t value. T is nothing but a u. So here also the t is varying from 0 to 1 only, but it is interpolating 3 points. It is making use of 3 points to generate the curve. Similarly, if you take a cubic Bezier curve, now it takes care of 4 control points. You can understand one more thing, that the curve always passing through the first point and end point. And another thing that you can observe is the curve is tangent to the, look at here, let me use the pointer. Look at here, P0 P1 is it's a straight line, and P2 P3 is another straight line, and the curve is tangent to the first segment P0 P1 and similarly it is also tangent at the last segment P2 P3. So that is how, that is another characteristic of the Bezier curve. Not only passes through the first and end point, but also would maintain the tangency. And by drawing, by imagining another straight line connecting from P0 to P3, connecting from P0 to P3, now you can imagine P0, P1, P2, P3 as a polygon, right? And that polygon is called as a Bezier polygon. That polygon, imaginary polygon, is called as a Bezier polygon, which comes by joining all the control points. By joining all the control points, you can imagine a Bezier polygon. So here one more thing that you can understand, and another characteristic is the curve always lies within the Bezier polygon. The curve always lies within the Bezier polygon. And of course, there are certain other things also need to be understood about Bezier polygon. Okay, we will talk about convex hull property, all those things. Okay, and similarly, if you take many more points, like if you take 5 points, how the curve is how the curve is behaving, try to understand that red colored one. So you should understand that each and every point is influencing the each and overall shape of the Bezier curve, which means if I simply pick the point P1 and drag to some other location, that movement, that relocation of any one point, it alters the overall shape of the Bezier curve. So it comes under global control. The Bezier curve, another characteristic of the Bezier curve is global. It is having global control rather than a local control. Okay, and similarly, if you imagine uh, fifth order Bezier curve, which means fifth order means the degree of the equation would be the highest degree of the equation, parametric equation would be 5. Okay, but in order that is possible, if you take the number of control points as 6. Always the degree of the equation would be number of control points minus 1. Okay, always the degree of the equation. For example, if you take the first one, I'm using 2 control points, so the degree of the Bezier curve equation would be only 1. Similarly, if you take 3 control points and try to develop a Bezier curve, the degree of the equation would be 2. 3 minus 1. Similarly, 4 minus 1, you get a cubic Bezier curve. 5 minus 1, you get a quartic Bezier curve. Similarly, if you take 6 points and try to generate a Bezier curve, degree of the equation it uses would be of the order of 5. Okay, and here here itself I can say that the Bezier polygon would be not only by simply joining the first and end points, but also Bezier polygon, all the extreme points should be joined. All the extreme points, these are the extreme points, right? So now by joining by imagining all the extreme points were joined, now the entire curve comes within that Bezier polygon. Is this clear to you? Okay, so always it never goes out of the Bezier polygon. Curve always lies within the Bezier polygon. And now if you try to analyze some of these pictures, so as an example, let us take quadratic and cubic Bezier polygons to understand how the geometry behind these Bezier curves. So if you look at P0, P1, P2, these are the points that I am picking in the on the screen. These are the 3 input always takes it takes points as the input. Whereas if you look at the Hermite cubic spline, it is taking endpoints and tangent vectors. Tangent vectors are not control points; they are different, right? Whereas here, if you look at the Bezier curve, I am directly entering the various points. It simply takes all the points as the inputs. So now P0, P1, by joining P0, P1, I can imagine a straight line. P1, P2, I can imagine another straight line. So at a particular t value, which means t is equal to 0.25 or u is equal u is equal to 0.25, which means this shows you the point q naught, at t is equal to 0.25, q naught lies on p naught p1 straight line, and q1 lies on p1 p2 straight line. q1 it moves from p1 to p2. q1 moves from p1 to p2, whereas q0 moves from p0 to p1 with respect to the t value. So if t value is 0, then q0 will match to p0, q1 matches to p1. If t is equal to 1, then q0 matches to p1, q1 matches to p2. So in between, what will happen? T varies from 0 to 1. For example, if t is equal to 0.25, nothing but 1/4. So then q0 would also be at 1/4 of the length of the p0 p1. Similarly, q1 would be a point which gives us the 1/4 distance of 1/4 distance of p1 p2 straight line. So now you can imagine at any point, at any t value, you can imagine how q0 how you can imagine the position of the q0 as well as q1. So as an example, he took t at an instant t is equal to 0.24, q0 and q1 positions are shown with green color dots, and by joining these two green color dots, green color line, I can form green color line, right? So now again this q0 q1, again if you apply t is equal to 0.25, then you can get a point called b. You can get a point called b, which means b is also 1/4 of q0 q1, and that b is also varying from b is a point. This particular b is a point, and this b gives you the point on the Bezier curve. So when q0 is changing, when t is changing, automatically q0 is moving, q1 is moving, and then correspondingly the point b also moves. So if you now if you record all the points b for various t values, then the point b moves in the direction of this particular red colored curve. So this red color curve is called as a quadratic Bezier curve. So each and every control point is influencing the shape of the quadratic curve. Similarly, if you try to understand cubic Bezier curve, which I can attain by making use of four control points, then also you can perform the same task at a t is equal to 0.25, identify q0 on the line p0 p1, identify q1 on the line p1 p2. Similarly, q2 also I can identify. These are the only straight lines right now, right? Because I haven't joined p3 p0, I haven't joined. But if I provide one more point p4, which is also matching to p0, then I have to draw the line here also. That is also possible. But if initial and final points are matching, then you get a closed Bezier curve. Okay. So right now we are trying to discuss about open Bezier curves. So in open Bezier curves, all the lines you can imagine like this, and q0, q1, q2 you can imagine, and on a line segment q0, q1, again you can denote r0 and r1, right, at a t is equal to 0.25. And again I'm getting, so one more straight line, blue color straight line, I'm able to get it in case of a four control points, and that straight line also again further divide into 1/4 and get the point b. So now that point is taking now this is the point on the cubic Bezier curve. So when t is changing from 0 to 1, so correspondingly the final point b also changes and follows the direction of this red color curve and is called as a cubic Bezier curve. So this is the geometric way of understanding the shape of the Bezier curve. I hope it is clear to you. Now if you go back to all these curves, now you can imagine, look at the cubic Bezier curve, look at this cubic Bezier curve. So when t is varying from 0 to 1, how this black color dot, which is it is starting from p0, and it is taking care of all this effect of all the control points, and then finally merging to the final point p3 and maintaining the tangency to the first line as well as the last line of the Bezier polygon. Okay, is this clear to you? Are you following? Hello?
Yes, sir.
Okay. Why? Because I can't switch the window to chat. Even if you put the messages, I cannot see right now. Wait. So now, if you try to understand the parametric equation, the mathematics behind this cubic Bezier curve, okay. As I told you, cubic third order equations would be sufficient enough because they can satisfy the needs of the C2 continuity. Okay, in order to make use of the C2 continuity, at the minimum order that we need to consider is the third order. Okay, so that is the reason we are always trying to understand the cubic Bezier curve, and similarly Hermite cubic spline only. We are not going beyond that or below that. Okay. Now, cubic Bezier curve, if you try to understand, as I told you before, cubic Bezier curve, in order to understand cubic Bezier curve, you need to have 4 control points. The number of control points are nothing but the number of the order of the equation plus 1. Okay. So, the parametric equation for any kind of Bezier curve is like this. Any kind of Bezier curve is defined like this. For any kind, in the sense, for n plus 1 control points. If the number of control points are denoted by n plus 1, then the generic parametric equation is this one. P of u is equal to sigma I is equal to 0 to n bin of u into, this is not x, this is into, okay, into pi, where u is varying from 0 to 1. This is a generic form. Whereas if you want to understand the cubic Bezier curve means the number of control points are 4. So n plus 1 is equal to 4, right? N plus 1 is equal to 4, which means n is equal to 3. Or I can also rather, which is nothing but, if the overall number of control points are denoted with n plus 1, the order of the equation is nothing but n. Simply saying, the order of the equation is simply nothing but a n. So as a cubic equation, if you want to understand the cubic Bezier curve, the order of the equation is nothing but cubic. So n is equal to 3. So the parametric equation will become sigma I is equal to 0 to 3 bi n bi3, I is a variable, right? N is a fixed one, n is equal to 3, right? So bi3 of u multiplied by pi. This bin of u, it is called Bernstein function. It's called Bernstein function. Okay, bin of u is called as a Bernstein function, and which will have its own formula like this. Bin of u, it's the Bernstein function you can calculate by using this formula n factorial by n minus I factorial into I factorial multiplied by u to the power of I into 1 minus u to the power of n minus I. I want you to remember this Bernstein function. Okay. Of course, the above one also you should remember, but it is somewhat easy compared to this formula. So here itself you can remember it. So generic parametric form of Bezier curve is P of u is equal to sigma I is equal to 0 bin of u into pi. Now, if you want to expand this generic form, if you want to apply for cubic Bezier curve where n is equal to 3, right? Where n is equal to 3, if you try to expand that, then what will happen for what will happen? We will try to understand. So for 4 control points, basically for 4 control points, how the curve looks like. So P naught is 1 point, P1 is another point, P2 is the third, P3 is the 4th control point, and U is varying from 0 to 1, starting from the first point to the end point. So in this case, how the parametric equation will become? It is simple. Look at here. I is equal to 0 to 3, n is equal to 3, right? And bin, this n is nothing but 3. So if I expand it, what will happen? Uh, P of u is equal to, if you try to expand this equation, what will happen? P of u is equal to, P of u is equal to, you know, sigma I is equal to 0 to 3, right? So b I 0, I is equal to 0, right? N is equal to 3, right? So b 0 comma 3, 0 comma 3 of u, this is one Einstein function, okay, multiplied by pi, I means 0, so p naught, p naught multiplied by p naught. So this first one, okay, leave about p naught. P naught is a different term, whereas b03 of u is another term. So this term is a Bunsen function. Similarly, plus I need to apply that sigma, right? So the next one will become b1 comma 3 of u multiplied by p1. All these p0, p1, p2, p3, they are the control points. So Bernstein functions do consider each and every control point. They become the coefficients of the each and every control point. So similarly, you can understand, the equation, the oral equation will become like this, right? The oral equation will become like this. P of u is equal to P naught B03 u. This P naught, he just moved to the front. So P naught B03 of u. So this reduces some confusion, right? So all the points he moved to the front. So P1 B13 of u. So this is B13 of u. P1. Similarly, apply 2 also. P2 B23 of u. B33 of u. So now I need to calculate all these Bernstein functions, right? So how to calculate these functions? So use this formula. Use this formula. For example, if you want to calculate B03 of u, so go to the next slide. So this is the formula, right? This is the expansion of the sigma form for cubic Bezier curve, and this is the Bernstein function. Now if you try to calculate B03 of u, so what do you mean by, if you look at the formula n factorial by n minus I into I, right? I is equal to 0 here, n is equal to 3, right? N is equal to, so 3 factorial by 0 factorial means 1 only. So 3 minus 0, 3 factorial. So 3 factorial by 3 factorial, and u is a variable to the power of 0, u to the power of 0. 1 minus u to the power of 3 minus 0, 3. So I am getting, this is a 1. Final value is 1 minus u to the power of 3. This is the first Bernstein function B03 of u, which should be applied to P naught. Which should be this function to be applied to P naught. Similarly, you need to calculate B13 of u, B23 of u, B33 of u also. You can calculate like this. Look at here, B13 of u. Now instead of I, you simply replace I with a 1. N is always 3 only for a cubic Bezier curve. So the equation, the Bernstein function will become 3u multiplied by 1 minus u to the power of 2. Similarly, B23 of u and B33 of u, all the Bernstein functions you can calculate, and then you have to apply these final values. All these final values you have to apply, you have to put it back in the parametric, the expansion of the parametric form for the cubic Bezier curve, and then the equation will become like this. Look at here, P naught multiplied by 1 minus u to the power of 3, P naught multiplied by 1 minus u to the power of 3. Similarly, P1 multiplied by this 3u into 1 minus u square. The 3 is a constant, which is moving to the front. 3p1 u into 1 minus u square. Similarly, that is how the entire, this is the final parametric equation of the cubic Bezier curve. Final parametric equation, okay. You should remember this equation. for solving the problems, you need not derive all this entire equation from the beginning. It's not required. Why? Because all the questions do come from the for the cubic Bezier curve only, whose parametric equation was just now derived. So if you can remember this equation, that would be more than sufficient. So P naught, look at that equation. P naught is the first one, and P1 comes in the second term. P2, P3 comes. So there are totally 4 terms. Each is having the points P naught, P1, P2, P3 for each term, right? Uh, Now the coefficients of P naught, P1 minus U to the power of 3, 1 minus U whole cube, and 3U into 1 minus U square, 3U into 1 minus U square. Look at this. This is the second coefficient. Second coefficient. This is the third coefficient. This is the fourth coefficient. I want you to remember. So the power of u is 0 in the first term, whereas power of u is increasing 1, 2, 3 like this. Whereas power of 1 minus u is decreasing, starting from 3 to 2, and then 1, and finally 1 minus u to the power of 0. So if you can easily remember like that. On top of that, you get 3 values, the numbers 3 for the second and third terms. That is how you can remember the overall parametric equation. And in some of the books, the matrix form also would be mentioned, and some of the problems you may need to solve using matrix form also. So the same parametric equation, you can also, write a parametric form like this. Look at here. This entire equation, you can also rewrite in matrix form like this. So how do you justify this matrix form? So for that, if you want to understand how both these equations are same, if you want to know that, try to expand this 1 minus u whole to the power of 3, 1 minus u whole cube. You know the equations, right? A minus b whole cube, right? A cube minus 3a square b plus 3ab square minus b cube. So if you apply that equation and then expand all these 1 minus u whole cube, 1 minus u whole square, all these, if you multiply all those things, and then if you try to understand, look at here. This is a horizontal row and this is a vertical row, right? So u cube would be multiplied with a minus 1, u square 3, u minus 3, 1, 1. So I can write it like this: 1 minus 3u, okay, 1 minus 3u plus 3u square plus 3u square minus 1. This is actually minus u cube, sorry, minus u cube. This is actually is equal to 1 minus u whole cube. This is actually equal to 1 minus u whole cube, which is same as this one, right? So that would be, the first horizontal row, first vertical column, that would be multiplied with the P naught, right? So that is what shown here. So this parametric, the expansion of this parametric equation can also be written in matrix form like this, using one horizontal matrix, one square matrix, and one vertical matrix. So by doing this, I'm able to separate the parametric. The first matrix is called as U parametric matrix. The second square matrix is called as a Bezier matrix. The third matrix is called as a geometric matrix. Why? Because all these P0, P1, P2, P3 are the input parameters which I am supplying as a geometry to the generation of the Bezier curve. So I am able to separate all these matrices, all these various values. I am able to separate it successfully. That's the reason it would be easy for me to solve the problem in the matrix form. So you can understand U is called as a parametric U matrix. BM is this square matrix called as Bezier matrix. The last matrix, the column matrix is a geometry matrix. Okay. I also want you to remember this Bezier matrix. In the previous class, you try to understand Hermite matrix, right? HM denoted with HM, Hermite matrix, which is in well, that is also a square matrix, but the values are different. Okay, so here also square matrix minus 1 3 minus 3 1 3 minus 6 3 0 minus 3 3 0 0 and 1 3 zeros, and all these values are simply zeros. Actually, all these values are simply zeros, and remaining things, if you can remember, that would be, so the minus is actually this minus plus minus plus, right? That is keep changing, plus minus plus minus plus. So you can remember these values in your own way, right? Now coming to Bezier blending functions, as I told you, blending functions are nothing but these 1 minus this is the final parametric equation of the cubic Bezier curve, right? So these coefficients 1 minus u whole cube and 3u into 1 minus u square, the coefficients of all these control points are called as blending functions, which influence the overall shape of the curve. Why? Because if the 1 minus u uh, whole cube, if this value is more, then p naught influence would be more on the curve, right? So that's why in order to understand the overall shape and the influence, people do try to understand the blending functions as well. So the blending functions, if you try to look at if you draw graph for each and every blending function, for example 1 minus u cube is nothing but b03. Okay, this 1 minus u whole cube is nothing but b03, denoted with the b03. Similarly 3u into 1 minus u square, that is denoted with the b13, the coefficient of p naught, nothing but 3u into 1 minus u square, so that is denoted with b. So similarly the coefficient of p2, coefficient of p3, all the different blending functions. And b03, the graph for b03 looks like this. It is starting from 1 at u is equal to 0. Okay, this is u. The x-axis shows you the u value. U is varying from 0 to 1. So when u is varying from 0 to 1, then how various blending functions are varying and their influence you can understand. Okay, so from here, from the blending function, I can understand that at any value of u, blending functions are non-zero. At any value of u, blending functions are non-zero. Okay, except except at u is equal to 0, except at all blending functions do have certain positive values. Okay, when u is varying from 0 to 1. At any value of u, the sum of the blending functions is always 1. What do you mean by this? For example, let us take at u is equal to 0.1. So at u is equal to 0.1, you do have certain b33 value, b23 value, you get another value, and similarly b13 you get another value, b03 is another value. So all these points do denote the values of the blending functions corresponding to u is equal to 0.1. But now if you add all these values, the final value would be 1. So that is what he is telling you about the characteristics of these blending functions. Similarly, you can take any u value, you can take any two value. For example, 0.6 at u is equal to 0.6, you have certain value here, you have a certain value for b33 here, another value for b13 here, another value for b23 here. Now add all these four values, final value will become 1. So that is what another characteristic of the Bezier function. Now curve is symmetric with respect to u and 1 minus u, which you can understand. b13 and b23, they are inverse. Okay, they are mirror images. So which means if you take if you imagine a straight line at u is equal to 0.5 as a mirror line, all these curves, for example b03 is mirror image to b33. These two are the mirror images with respect to a center line u is equal to 0.5. Similarly, B13 and B23, these curves also mirror images with respect to u is equal to 0.5 line. So that is the reason the overall curve also do follow symmetry. The overall curve also do follow symmetry, which means the influence of uh, uh, even if you alter the sequence of the points, even if you alter the sequence of the points, the overall curvature of the overall shape of the Bezier curve would be the same. So that's what the meaning of the symmetricity means here, which means P0, P1, P2, P3, by picking points P0, P1, P2, P3, 4 points, and then asking to draw the Bezier curve, whatever the curve that you get. Similarly, rather than picking those points in this sequence, you can also pick the sequence in another way, like instead of pick P4 as the first point, P3 as the second point, P2 as the third point, P0 as the fourth point, which means the sequence I just changed, but still the overall shape would be the same. Why? Because of this symmetric property of the blending functions. Okay. Now let us try to solve an example. What's the time? Okay, 9:49. Let us try to solve a problem. A cubic Bezier curve is defined by control points. So here, 4 control points are given: P0, 1, 1, P1, 2, 3. 4 control points are given, and z coordinate is not given, which means the entire Bezier curve is lying in a xy plane. So no need to give any z coordinate, which means the entire curve, each and every point lies in. This is a coplanar curve. Coplanar curve means even the overall curve was lies on the same plane. Okay. Now for this, he is asking you to, given 4 control points, try to you need to develop the cubic Bezier curve. Okay, cubic defined by the, find the equation of the curve, and also its midpoint. So we know the parametric equation, parametric form, we know sigma is equal to 0, and its final expansion also just now we understood, P naught into 1 minus u. Now if you write everything in terms of P, that is a generic parametric form. The same thing, if you want to, you can also write in a scalar form. There is another form called as a scalar form or algebraic form in certain textbooks. So the same parametric form in scalar form, you can write it like for x, you will get x equation, and you can also write a y equation separately. Nothing but x of u is equal to, instead of p naught, it will be x naught. X naught into 1 minus u whole cube 3 x1. What do you mean by x naught and x1? X naught, x1, x2, x3. All these are x coordinates of the points. X coordinates of the points, 4 points. So that is how the scalar form you have to write the scalar form, and in order to calculate all the points. Okay, simple parametric form, you cannot directly use the generic parametric form to calculate the various points. Ultimately, you have to convert it into scalar form and then calculate all the various points on the Bezier curve, or as you desire. Just like in this question, it's you want to calculate midpoint, right? So whenever you want to find out points on the curve, you need to make it with the scalar form. Scalar form also comes from the parametric form only. Only thing is all the p's would be replaced with the x's, either x's or with the y's or with the z's separately. So x of u will become x naught, 1 minus u. P1 will become x1. So all these things you can observe. Now substitute all these x values. X naught is equal to 1, x1 is equal to 2, this is 4 and 5. And now substitute all these values, and also he is asking you to calculate the midpoint. Midpoint means actually u is varying from 0 to 1, right? So for midpoint u is equal to 0.5, right? So in the scalar form, if you want to calculate x is equal x coordinate of the midpoint, nothing but x of 0.5. So x naught is equal to 1. X naught is equal to 1. 1 into 1 minus u whole cube. Here u is equal to 0.5. Similarly, 3 into x1 is equal to 2, right? 2, 3 into 2 into u into 1 minus u square. Again, instead of u, you have to substitute 0.5 to calculate a midpoint. So finally, you are getting x coordinate of the midpoint as 3. Similarly, y coordinate also you can write another y equation from the same p of u equation. Only thing is, instead of p, you have to write a y values here. All these are the y coordinates of the 4 points, right? So similarly, you can also calculate the y coordinate of the midpoint as 2.5. Therefore, the final midpoint of the, here what is the equation of the curve? This is the equation of the curve, right? This is the equation of the curve. And what is the midpoint? What is the midpoint? 3 comma 3 comma 2.5 is the midpoint of the Bezier curve. 3 comma 2.5. This is the midpoint, right? I hope it is clear to you. Similarly, one more problem. This problem we try to solve with the help of a matrix equation. Okay. Here also 3 points are given to you. All the z coordinates are 0. So nothing but the case of a xy plane only. But as he gave z coordinates in the question, while solving also you can make use of all these values as it is. Okay, he gave those values in the question. So in the answer also try to make use of those values. Even if you remove it, it's not a problem. It's not wrong. Okay. For all these 4 points, you need to find out the equation of the Bezier curve, and then not only the midpoint, he is asking you to find out more number of points at u is equal to 0, at u is equal to 1 by 4, 1 by 2, 3 by 4, 1. But he is asking you to find out 4 points on the Bezier curve. But frankly speaking, out of 4 points, you already know the 2 points. Why? Because at u is equal to 0, at u is equal to 0, what do you mean by u is equal to 0? The curve is passing through the first point, right? So obviously at u is equal to 0, the point you will get 2, 2, 0 only. Similarly, at u is equal to 1, which is nothing but the final point on the Bezier curve, which is nothing but the curve passes through the final endpoint, right? So at at u is equal to 1, even if you calculate it, you get this value only, 3 to 0 only. So you can simply write this and you can write this as a sentence, and then you can simply give the values, or else you can try to solve it also, no problem. But whereas for 1 by 4, 1 by 2, 3 by 4, you have to calculate. So in matrix form, this is the matrix form, and then here what I need to do is all these P0, P1, P2, P3s, I have to this matrix P instead of P0, 2 to 0. This is P0, this is P1, P2, P3. So this is the matrix. This is a 4 by 3 matrix, and then multiply. If you multiply, ultimately, you get a 1 by 3 matrix. Final matrix would be 1 by 3, out of which this denotes you the x of u equation, this denotes you the y of u equation. Z of u is equal to 0. As I told you in the question itself, all the z coordinates are 0. So always the z coordinate would be 0. That's why you are getting a constant 0 here. It's not a function of u. Whereas this is x of u function, this is y of u function, right? So if you want to calculate at u is equal to 0, if you want to calculate, substitute u is equal to 0 in this matrix. So u is equal to 0, if you substitute it, finally you are getting 2 to 0, nothing but p naught value. Similarly, at u is equal to 1 by 4, all these values you can calculate. So these are the intermediate 3 points, and 3 to 0 also the final point. So I hope it is clear to you. And the characteristics of the Bezier curve, drawbacks, all these things we try to discuss in the next class. Okay, time is up, right? So let me take the attendance.